time to do some more problems. And I will say that the next set of problems are the harder problems. Um, I don't want to make it sound like they're too hard, but they require a little bit more thought, a little bit more care. That's okay. We can still do it. We are capable. And by doing hard problems, we learn. In fact, when we often do hard problems, it makes the easy problems even easier because we start to spot the patterns and the ideas, and it becomes beautiful. So beautiful. All right, well, let's get going. So, consider the initial value differential equation. 2x y prime plus y squared minus 3x squared equals 0. Y of 2 equals 3. And we're going to find a solution, and we're going to do it in 3 different ways. And I think the point of this problem is just to say, you sometimes have options. And so don't be like, what is the way to solve a problem? Well, maybe there's not the way, but maybe there are many ways. And so the key is find one, and find one that works for you, that you're comfortable with. All right, so here we go. We're going to do this problem 3 times. The nice thing is we can compare answers, and they should all be the same, right? Because there's just one solution. If we're getting less than, if we're getting 2 different solutions, something's wrong. All right, so part A. Using that this is an exact equation. All right, so how does that work? So if you look at this, you say, look, we can rewrite this as 2xy dy plus y squared minus 3x squared dx equals 0, where we think of this as dy dx, where we separate the dy dx and multiply it by dx. All right. Well, if we're thinking this is exact, and it says it is, then we say, okay, this first piece here, this would be the derivative of what we want with respect to y, because that's what the dy is telling us. And this piece over here is the derivative of what we're after with respect to x. So we have those derivatives, so we integrate. So our function that we're after, well, it's the integral of 2xy dy, which means that we treat y as a variable and x a constant. And so that would be xy squared plus some arbitrary function of x. Well, I shouldn't say some arbitrary, but some function of x. And in a similar way, well, we integrate y squared minus 3x squared dx. So now y's are constants, x's are variables. So the integral of y squared, or that's like the integral of a number. So that would be y squared times x, or x y squared, integral of 3x squared, x cubed, and then some function of y. All right, so far so good. Now we do our quick spot check. Okay, so what's that? Well, we look at the pieces involving both x and y. We say, do they match? They do. And then there are the other pieces. And in this case, there's just one other piece which only involves x. There might be pieces that only involve y. It depends on the problem. Say, okay, perfect. That says we are dealing with something exact, and therefore we can put it together and say our function has the form of xy squared, this piece here, minus x cubed. Now, if it's exact, that's going to equal some constant c. The only thing left for us to do is ask, what's the constant? All right, so to do that, plug in the values. So we're going to plug in x equals 2, y equals 3. So we're going to get 2 times 3 squared, so that's 18, minus 2 cubed, which is minus 8, equals c. So that says c equals 10. And therefore, our final answer, x y squared minus x cubed equals 10. All right. Done. Part A. Now, part B says, hey, actually, maybe you didn't see it was exact, but you looked and said, look at my pieces. I have a square, and x times y, which basically means it's like a square, right? Degree 2. Homogeneous. Okay, so what happens? Well, we say, look, we're going to divide everything by x squared. Okay, and why x squared? X is our independent variable, and squared because all these terms are square terms. So, divide everything by x squared, we get 2 y over x, y prime, plus y over x squared minus 3 equals 0. And our substitution, well, that's v equals y over x. So we say y equals x times v, which tells us that y prime, well, that's going to be v plus x v prime. So we now know how to do our substitutions here. So updating, we say, all right, this will become 2 times v plus x v prime plus v squared minus 3 equals 0. All right, well, let's see what we have here. We can do our distribution. So we'll have 2v times v, that's 2v squared plus v squared. That makes 3v squared. Then there's minus 3. Then there's plus 2xv v prime equals 0. All right. Well, now what? Well, okay. Now we can say the following. We can move this across. So 2xv v prime is equal to 3 minus 3v squared. Or, now we do our separation. So we can divide by 2v. Well, actually, we'll divide by x. Here we'll divide, 1 minus v squared. So I'll write it in the following way. So 2v over 1 minus v squared. Notice that this side is 3 times 1 minus v squared. And dv is equal to, on the other side, we'll have 3 and over x dx. All right, great. Now you might be getting nervous like, oh man, we got to do partial fractions, right? No, we don't have to. Take a look. Don't get discouraged and say, bite the bullet. No, because what can you do? If you look at the denominator, 1 minus v squared, what's the derivative of that? Well, it's minus 2v, which is essentially the numerator. So we say, okay. So let's just run that through. So du is minus 2v dv. I can move the minus across. So that this would become integral du over u, which is log u. Well, with the minus. I should forget the minus. Okay. So that's how you handle the left-hand side, which of course, that's minus log 1 minus v squared. So we have minus log 1 minus v squared equals 3 natural log x plus c. Okay, great. This is a wonderful, wonderful progress. Okay, where to next? Well, the next thing is, let's get rid of our logs. Okay, so we're going to take both sides to the e power. So here we'll have 1 over 1 minus v squared, because the minus means it's 1 over. On this other side, e to a constant is a constant, and here the 3 comes up, so that's x cubed. All right. Or we could say that 1 is equal to some constant x cubed times 1 minus v squared. But what is v squared? Or what is v? V is y over x. So this would be y over x squared. All right, great. Well, let's clean it up a little bit. How can we clean it up? Well, one way we can clean it up is multiply through. So we'll get 1 is equal to some constant x cubed. And now, notice what happens here. We have an x cubed, x squared. So we'll just have some constant x, y squared. Now you notice here, these are both constants. So one thing we can do is we can move that constant. We could have actually divided by the constant, move it across. So we could say, oh, this is really the same as x cubed minus xy squared equals a constant. And now, what do we need? Well, we need to solve for our constant. And, okay, we'll plug it in. So we'll have 2 cubed, which is 8, minus 2 times 3 squared. That's 2 times 9, that's just 18, equals our constant. So our constant is negative 10. So we end up with x cubed minus xy squared equals negative 10. And they match. Or you might say, no, they don't. Well, they do up to a simple sign change. So yeah, they match well enough. And now we have the challenge. We run out of space to do it the third way. But that's okay. You know, just have some scratch paper nearby. I happen to have some scratch paper here. And we'll do it in the third way. Okay, so we're going to do it again. It says, hey, make a substitution. Y squared. And let's see what happens. So we'll have v equals y squared, v prime, 2y, y prime. And then we're like, whoa, 2y, y prime. That sounds really familiar. So in particular, notice our first term. We can write that as x, 2y, y prime, plus y squared minus 3x squared equals 0. So this 2y, y prime, that's v prime, and the y squared, that's v. So we're x v prime plus v, and we'll move the minus 3x squared across. So equals 3x squared. And that is nice. It's actually beautiful because it's a first order linear differential equation. Okay, so we say, all right, what needs to be done? Well, we have a small issue. There's an x there. Uh-oh. Shouldn't have that. Okay, so what do we do? Well, if we're going through the process, we would divide by 1 over x, or multiply by 1 over x. So we have v prime plus 1 over xv is equal to 3x. And then we look at this piece. This is going to be our integrating factor, e to the integral 1 over x dx. Well, of course, that's e to the natural log x, which is x, which means multiply everything by x, which says, hey, we should have it as x v prime plus v equals 3x squared. And now we're like, what? That's what we just had. Well, but now we say, we know, we know something here. What we know is that this side is a derivative. And so this is the derivative of x times v. And now we're like, wow, great. So we integrate both sides. And of course, the left hand, super easy. That's the by design that it should be super easy. So we have x times v equals integral 3x squared, x cubed plus c. And now, to finish, put in what v is. X y squared equals x cubed plus c. So we need to find c. Well, our initial conditions, 2, 3. So we'll have 2 times 3 squared, 18 equals 2 cubed, 8 plus c. So c has to be 10. So finally we end up with xy squared equals x cubed plus 10. And you'll notice, again, we match. So all three techniques, we all ended up with the same answer. Coincidence? No. If we hadn't, we'd be like, oh man, we got to do some more work. More work. But for now, we're happy. What a wonderful way to start. Nice warm-up problem for number 1. Okay, let's move on, if we can, to number 2. And this one seems pretty straightforward. No big surprises. It's about the Wronskian. So the Wronskian is a tool, and it's related to linear independence. In this case, it just says, compute it. We don't even have to make any conclusions. It just says, do the computation. So this is a good chance for us to review how do we do Wronskians. So we take our 3 functions, e to the x, sine of x, cosine of x, and what we do is we make a nice little matrix, and we're going to take the determinant of this matrix. The first row are the 3 functions, e to the x, sine of x, cosine of x. For the next row, take derivatives. Derivative of e to the x, e to the x. Derivative of sine, cosine. Derivative of cosine, negative sine. All right, now for the next row, take the derivative of the row above it. Derivative of e to the x is e to the x. Derivative of cosine, negative sine. Derivative of negative sine, negative cosine. So we set up our little matrix here, and we're going to take the determinant of this. Now you can do it by cofactor expansion or diagonals. And diagonals work if you're dealing with something which is, say, 3 by 3 or 2 by 2. And on an exam, we would not ask you to do 4 by 4. So here we go. I'll do diagonals. I like diagonals. So we have e to the x times cosine x times minus cosine x. So that would be minus cosine squared x e to the x. And we'll have sine of x times minus sine x times e to the x. So that's minus sine squared x e to the x. And then we'll have a cosine e to the x and a negative sine. So that'll be minus sine x cosine x e to the x. All right, so those are the down diagonals. Now the up diagonals. E to the x, cosine x, cosine x. So that would be cosine squared e to the x. Remember, when we go down, add, up, subtract. So subtract cosine squared x e to the x. Then the next one, negative sine, e to the x. Well, that'd be sine squared e to the x, but we have to subtract that. So minus sine squared e to the x. And then we have minus cosine e to the x positive sine, but we have to subtract that. So minus and minus makes a plus cosine x sine x e to the x. And now we have our great And in fact, a couple of things happen which are really nice. We get cancellation there. What else can we say? Well, we can factor out, we have 2 cosine squareds, and here's 2 sine squared, so we can actually factor out minus 2 e to the x, because there's doubled, the minuses and the e to the x's. And then we have cosine squared plus sine squared, also known as 1. And so we get minus 2 e to the x. And that's as simple as we could hope for. Now, it didn't ask us the punchline, but the punchline is that's not a zero function. And it's never zero, actually. It's never zero anywhere, which means that these are really nice functions in the sense that they're linearly independent. Yay! That means they're all contributing to something different, which is a wonderful thing to do. Now, you might have a question which says, did we have to actually simplify? Well, this gets into sort of a gray area for me. And I would say that if there's simple simplifications, you should be polite and do those. But if there's hard simplifications, unless they tell you to simplify, you should be okay if you don't. Because you can argue, I followed the instructions, and the instructions did not specify to simplify. So, all right. Well, that was the Wronskian. On to number 3. solve the initial value problem. It's a third derivative. So the third derivative of y plus 2 times the second derivative of y minus 4 times the first derivative of y minus 8y equals 0. And then there's some initial conditions. What happens to the function at 0, the derivative at 0, and the second derivative at 0? All right. Now this is our favorite kind of problem. It's constant coefficient, linear, homogeneous. This is like, we know how to solve these, assuming that we can actually factor. But, sure we can, right? Okay, so how do we go about solving this? Well, we start by saying, okay, we translate our differential equation, y triple prime plus 2y double prime minus 4y prime minus 8y equals 0 into an algebra equation, r cubed plus 2r squared minus 4r minus 8 equals 0. All right. And now we say, aha, we just have to factor that. And you might be like, yeah, we do have to factor that. How do we go about that? Because it's a cubic, so we don't have a formula for that. So this is where we have to be a little bit careful. And what can we do? Now, there's sort of two approaches. One approach is to say, can we find sort of like natural groupings? So what is that? Well, notice if I group in pairs like this, what would happen? Well, here we say in this grouping, I can factor out r squared, r plus 2. Over here, I could factor out minus 4, r plus 2. And then we're like, whoa! Because we see r plus 2 is common. And so this becomes r squared minus 4. Or we say, look, we can actually factor r squared minus 4. That's r plus 2, r minus 2. And we're done. Now, grouping sometimes works, sometimes doesn't. And sometimes you have to have just sort of the right kind of equation. So, okay, what if it hadn't worked? What could we do? Well, the answer is we could guess. So what are some natural guesses? Well, since this is a 1, the guess has to be something that divides into 8. So plus minus 1, plus minus 2, plus minus 4, plus minus 8. Those are the only nice roots that this can have. And by nice, we mean whole numbers. Actually, technically, it's nice means rational. All right, so we can just try things like 1. Okay, 1 plus 2 minus 4 minus 8. No, there's no way that's 0. Negative 1 minus 1 plus 2 plus 4 minus 8. No, not going to work. Okay, how about 2? 8 plus 8, right? 2 cubed is 8. 2 times 2 squared is 8. And then 4 times 2 is 8 minus 8. So it's 8 plus 8 minus 8 minus 8. It cancels. So we say, aha, r equals 2 works. And we're happy. Now, once you know r equals 2 works, then we can do the following. Take r minus 2 and divide. To r cubed plus 2r squared minus 4r minus 8. So let's see, you needed r squared, right? Because you look at leading terms. R times what gives r cubed? The answer is r squared. So r cubed minus 2r squared. Subtract. And r cubes cancel. 4r squared. All right. To get from r to get to 4r squared, we would need 4r. All right. So that would, now we multiply. That's 4r squared minus 8r. And let me move this up a little bit so we can finish it. Subtract and cancel. And here we'll end up with 4r minus 8. We say, oh, perfect. We need 4. And now we say, look, this is a piece, and then the rest of it looks like r squared plus 4r plus 4. And so we just factor that. Well, that's not so bad. It's r plus 2 squared. Okay, so those are the things we could have done. All right, so now we have our roots. So our roots are minus 2, minus 2, plus 2. So once we have our roots, then we can say, all right, that tells us that our solution has the form. So y is some constant, e to the minus 2x, because that's the first root, plus some constant. And here, oh, it's minus 2 again. Okay, so we need to bump it up. And then the 2, well, that's the first time we've seen 2, so that's some constant e to the 2x. And what we don't know is we don't know a, b, and c. All right, so we'll work on that. So what can we say? Well, let's take some derivatives for reference. Y prime minus 2a e to the minus 2x plus, now here I'll have b. Now when you take the derivative here, you have to do product rule. Derivative of the first would be 1 times e to the minus 2x, then it would be x, and then minus 2 comes down. So when you put them together, you'll end up with 1 minus 2x, e to the minus 2x, and then over here, 2c e to the 2x. Y double prime, all right, that'll be 4a e to the minus 2x plus b. All right, here we go again. So take the derivative of the first, that would be minus 2 times e to the minus 2x. And then we take the derivative of the second. Okay, the minus 2 comes down, so it'll be minus 2 plus 4x, e to the minus 2x. So when we put those together, what we'll end up with is we'll end up with 4x minus 4, e to the minus 2x. Here, 4c e to the 2x. All right, good. All right, now it's okay to be skeptical. Even me, I'm doing it, and I'm looking at this and being like, okay, is this right? So again, just work through it. Derivative of the first is 1 times e to the minus 2x. That's the first piece. And then derivative of the second, the minus 2 comes down. That's where the minus 2x e to the minus 2x comes from. All right, derivative of the first is minus 2. That's part of the minus 4, e to the minus 2x. And then here, that stays, and then we bring a minus 2 down, so minus 2 plus 4x. So that's the rest of the minus 4 and the 4x. So, good. Okay, so we have y prime, y double prime, and we need those because that's where we're putting our initial conditions in. All right, so here we go with our initial conditions. So we have that y of 0 is a, and then 0b, nice, plus c equals 1. Y prime of 0, okay, that's minus 2a, plus b, plus 2c, that equals 7. Y double prime of 0, that would be 4a, minus 4b, plus 4c, and that equals 0. Okay. Now, it seems like there's a lot of work going on here, but it probably isn't as bad as we think. Notice we see some 4's here. We say, hey, there's like 4's up here. So what we can do is we can multiply this last equation. Well, let's multiply the first equation by negative 4 and add it to the last equation. What would happen? Minus 4a plus 4a, 0. 0 minus 4b is minus 4b. Minus 4c plus 4c, 0. Minus 4 plus 0 is minus 4, which says, aha, b equals 1. Progress. Good progress, actually. Now, since we know b equals 1, let's put that into there. So we have minus 2a plus 1 plus 2c equals 7. or minus 2a plus 2c equals 6. All right, because we can subtract 1. Or we can say minus a plus c equals 3. It's divided by 2. On the other hand, we know a plus c equals 1. Added together. A's cancel. 2c equals 4. So c has to equal 2. All right. Well, now what? Well, we can plug it in. Say we plug it in here. A plus 2 has to equal 1. So we say, oh, all right, so a has to be negative 1. So we've solved for a, b, c. All right. So what's left to be done? Well, the answer is, the part that's left to be done is to write down the solution. So we know our general form. We know our constants. So we have that y equals a, which is minus e to the minus 2x, plus b, which is 1. So plus x e to 2x, plus c, which is 2. So plus 2e to, oops, there's a minus 2x there, 2e to 2x. Okay, well, I think the thing that makes this one hard is just 3 equations, 3 unknowns. And you're probably thinking like, that's a lot of equations, lots of unknowns. You'll look back on this and be like, I missed when we just had only 3 to do. All right. Back to our next problem. Solve the differential equation x squared y prime plus 2xy equals 5y to the 4th. Now, we look at this and we say, ooh, this feels like we see the y prime, we see the y. It feels like linear first order. The only problem here, like the thing that makes us say, uh-oh, is that there's this y to the 4th. Okay, so what happens here? Actually, what happens is we say we recognize what this is. This is a Bernoulli problem. So we say, yay, Bernoulli, Bernoulli. All right, so what do we do with Bernoulli? Okay, so this is one where we have that sort of a little bit unusual one. So if this is y to the n, our substitution we make is y to the 1 minus n, which in our case is 1 minus 4, or y to the minus 3. Okay, then we'll have that z prime is, well, okay, taking derivatives, minus 3, y to the minus 4 times y prime. Now, how does that relate to this original one? Well, divide everything by y to the 4th. And what you get is you get that x squared times 1 over y to the 4th, y prime, plus 2x, y divided by y to the 4th, which is, well, say y to the minus 3 equals 5. So, the y to the minus 3, that's our z, or z, if we want to solve it in a British way. And then here, say, ooh, that's almost our z prime. But we have to just sort of account for that minus 3. So that's minus a third z prime. Okay, so what do we have? When we carry out that substitution, minus 1/3 x squared z prime plus 2xz equals 5. And we're in linear first order in terms of z. So the Bernoulli substitution is to take something which is almost linear first order, other than this one piece, and turns it into linear first order. All right. So now we have to solve. Of course, when we're solving a linear first order, we come in front of our derivative term, we say, hey, we really want that to be a 1. It's not a 1 yet. So we got to make it a 1. All right, so, well, that's not so bad. We'll multiply by -3, divide by x squared. So we'll have that z prime. So multiply by -3 makes that -6. And we're dividing by x squared. So it's actually over x times z will be equal to, on that side, we'll have -15 over x squared. All right. Great. Okay. We're making wonderful progress because it's now in just the right form. So here we can find our integrating factor by doing e to the integral -6 over x dx. So that's e, well, this is a -6 natural log x, which becomes x to the -6 power. Or if you like, 1 over x to the 6. Okay, so we multiply everything by 1 over x to the 6. So we have 1 over x to the 6, z prime. And here we'll have -6 over x to the 7th, z, is equal to -15 over x to the 2 times x to the 6, x to the 8. Now, the nice thing is that this left-hand side, by design, this is a derivative. It's a derivative of your integrating factor times z. And you can check, right? All right. Keep the first alone, take rid of the second, then rid of the first, derivative of x to -6, the -6 comes down, drop the power by 1, so that was x minus 7 times z. Okay, so that's -15, x to -8. So we're going to integrate both sides. And let's see what happens. Well, let's see. Left-hand side, very simple. 1 over x to the 6 times z is going to be equal to, so we have -15. We're going to add 1, so that'll be x to the -7. Because -8 plus 1 is -7. And now divide by -7. And of course, add c. Well, 15 it doesn't go into 7, but that's okay. It doesn't have to. We're almost there. So let's multiply through by x to the 6. So we can say that z is equal to, multiply x to the 6. X to the 6 times 1 over x to the 7th gives us 15/7 times 1 over x. And then plus some constant, x to the 6. Now, what's our last thing to do? Well, what is z? Well, we can follow back. We say, look, z is y to the -3. So this is 1 over y cubed. So, in some sense, we're done, right? Say, look, this is a perfectly fine answer. If you are somebody who says, no, I really have to solve for y. Okay, flip both sides and take the cubed root. And so you get that y is 1 over the cubed root of this term, 15/7 times 1 over x plus some constant x to the 6. So that's another way to write the answer. Both are fine. Both should receive credit in my mind. All right, well, good. Halfway. Oh. Yeah, see, these weren't as bad as we were thinking. Well, we're still only halfway. All right. So number 5. A small 10-gallon tank initially contains brine. So think of this as salt water. And there's a total of 20 pounds of salt. So brine, which has 1 pound of salt per gallon, is being pumped into the tank at a rate of 2 gallons per minute. At the same time, the well-mixed, whoops, there's a typo here. It shouldn't be bring, it should be brine. We'll fix that later. In the tank is being pumped out at a rate of 3 gallons per minute. And the problem, will determine the amount of salt that will be in the tank when the tank is half empty. Oh, Man, whoever wrote this is a pessimist, right? Half empty. No. Half full. Yeah, that's the optimist way you'd write this problem. Okay, so, well, what do we have? So let's set S at any given t, time t. That's the amount of salt. All right, that seems a reasonable thing to do. And now we say, well, what do we know? So initially, there's 20 pounds of salt. So S at time 0 is 20. And now, the other thing we know is that things are happening. So our picture here, we have our tank, and there's stuff coming in, and there's stuff going out. All right, so what do we have? Well, okay, we can talk about our inflow. We know we have 2 gallons per minute coming in, because we're told that, and each gallon has 1 pound of salt. So we are adding plus 2 pounds of salt. So that's how we gain salt. Now our outflow, okay, we'll just make a little note here. There's 2 gallons. Now our outflow is what? Well, we're flowing out at 3 gallons. And, well, how much do we lose? Well, okay. Well, we lose. Well, okay, so. Sorry, I want to go slowly here because I don't want to make mistakes. You know, there's always that goal. Don't make mistakes. Okay, so we have to be careful here because the amount we lose depends on how much is in the tank. Because the amount of salt, if we had a very salty fluid, well, we lose a lot of salt. If we have a very unsalty fluid, we would not lose very much. So it depends on how much salt is in the tank. So we say, okay, well, how do we figure that out? Well, we say, okay, well, how much is leaving? And to figure that out, we say, well, let's look at the proportion. How much of the brine leaves? So in other words, like, what's the percentage of stuff that leaves? Well, we know 3 gallons leave, and we start with 10 gallons. It's a little bit ambiguous here, but let's just assume it starts with 10 gallons. I'll fix the problem right up after we're done. So we start with 10 gallons. We add 2 gallons and lose 3 gallons at the same time, which means that on a net flow of time, we are losing 1 gallon every minute. So we should say that the total amount of brine is 10 minus T. So what flows out versus how much is there in total, that's how much of the brine flows out. That's the percentage of the brine that flows out. So that'll also be the percentage of the salt that flows out. So the total amount of salt that flows out, we'll take that times S. Okay, so that's the net loss. So we know how we gain salt. We know how we lose salt. So there we go. So we put it together, say, okay, we have the following. S prime is 2 minus 3 over 10 minus T times S. All right. Good. Now, where to? Well, we need to know how much salt there is at a particular time, so we should solve. Okay. Well, this doesn't look so bad because we've done these kinds of problems. So let's do this kind of problem again. So we'd have S prime plus 3 over 10 minus T times S equals 2. So here's our integrating factor. So we want e to the integral 3 over 10 minus T dt. And you'll probably say, well, that's not so bad. That looks like natural log of 10 minus T. Right? Right? No. What are we missing? So this would be a common mistake here. What's missing? The minus sign. You got to account for that minus. So you have to put a minus there. Now if you're wondering, wait, why? Think about doing a substitution. U equals 10 minus t. Then du equals minus dt. So that's where the minus is showing up. Okay, so that really is, well, of course, the minus 3 is an exponent. So that's 1 over 10 minus t cubed. All right. So here we go. We are going to multiply everything by this expression. So we have that 1 over 10 minus t cubed times s prime plus 3 over 10 minus t to the fourth s is equal to 2 over 10 minus t cubed. And this side, by design, we've done this kind of problem before, that's a derivative. So it's a derivative with respect to t, 1 over 10 minus t cubed times s. And over here, well, let's prepare ourselves by writing it in a calculus-friendly way. So we integrate both sides. And what happens? Well, left-hand side, very straightforward. Over here, okay, we add 1 to the exponent, which makes it minus 2. Then we divide by that. So we have 2 over minus 2. And then we have 10 minus t to the minus 2. And we need another minus because of that minus on the inside. So that actually becomes a plus. And plus c. So to finish up, multiply through by 10 minus t cubed. And we'll move up here. So we say that the amount of salt at any given time t, well, that's a 1. 10 minus t to the minus 2, 10 minus t cubed will give us a 10 minus t plus some constant times 10 minus t cubed. All right. Now, what do we know? Well, we know that initially there's 20 pounds. So we have our initial condition. So, okay, plug that in. We'll have that 20, which is what happens at 0, is equal to what? Well, that's 10 plus some constant c times 10 cubed. Ooh, that's a big number. So, okay, so 20, subtract 10. Well, let's go ahead and do that. So 10 is some constant times 10 cubed. And then I can divide both sides by 10 cubed. So c is 1 over 10 squared, or 1 over 100. So we see our salt at any given time. That's 10 minus t plus 1 over 100, 10 minus t cubed. To finish up, when is it half empty? Well, we started with 10. If we're half empty, how much do we have? Well, we should have 5. Now, that's how many gallons we have, but be careful how much time has that been. And we are in luck. So here, it would be at time t equals 5. So plug in t equals 5. And we find our answer. The amount of salt, well, 10 minus 5 is 5, plus 1 over 100, 10 minus 5, 5 cubed. And if you wanted to, you could try to simplify this a little bit. So, for instance, you can say, look, that's 25 times 5 upstairs. It's 25 times 4 downstairs. So 25 times 5 over 25 times 4 makes that 5/4, or 6.25. And there we go. So there's 6.25 pounds of salt. Now you might say, is this reasonable? And well, we should think about it, right? So there's initially 20 pounds of salt, right? So if we emptied out half the tank, we'd expect to be about half as much. So 20 over 2 is 10. But think about what's coming in. The salt that's coming in, see here, it's a ratio 1 pound of salt per 1 gallon. But initially, it's 2 pounds of salt per gallon. So it's less salty water. So because we have less salty water coming in, we should expect that overall, we should have even less than just dividing by 2. So yeah, 6.25 is a little under 10, not too much. Seems like a pretty reasonable answer. So good for us. We got an answer. All right, well, on to another one. All right, verify that y equals e to the x is a solution of this differential equation. Xy double prime plus 3 minus 2xy prime plus x minus 3 times y equals 0. And use reduction of order to find a second solution. All right, well, verify. That's an important thing to be able to do. So how do you verify? Well, you plug it in. So x, e to the x, take the second derivative, plus 3 minus 2x, take the first derivative, plus x minus 3 of just the function. Well, the nice thing about e to the x is derivatives of e to the x look like e to the x. So it's very easy to do that. So what we really have is x times e to the x. This will be e to the x, so that'll be 3 e to the x subtract 2x e to the x. And we'll have here plus x e to the x subtract 3 e to the x. And now we say, okay, 3 e to the x minus 3 e to the x cancels. Nice. Well, we're anticipating that. No big surprise. Then you have the x e to the x's, and then there's a minus 2x e to the x. So those collectively also cancel. And so we're left with 0, which is what we want. So we're done. We verified the solution. All right. Now it says, hey, there should be 2 solutions because it's the second order. What's the other one? And, well, we're not going to just sort of like reach around in the dark. We're going to try to figure it out. So there's a certain technique, reduction of order. So how does that work? So the idea says, hey, we're going to make a new function called u. And we're going to, suppose we set y equals u times e to the x. So what we're really after is, what's this u? It's not a number, it's a function. So if we can find that function, then we say, okay, whatever u is multiplied by e to the x, there's our solution. So first derivative, well, product rule, u prime e to the x plus u e to the x. Second derivative, well, product rule twice, u double prime e to the x plus u prime e to the x plus u prime e to the x. I already have one of those, so I'll put 2 here, plus u e to the x. And now we're going to substitute in up here. So we have x times u double prime e to the x plus 2u prime e to the x plus u e to the x. So that's xy double prime plus 3 minus 2x times u prime e to the x plus u e to the x plus x minus 3 u e to the x. All right, and we're going to set that equal to 0. All right, because we're saying it's a solution. So we're saying, here's a new solution, and we're going to have to figure out what does u need to satisfy. So what we do is we do some grouping here. So let's see, u double primes, not very many, just the one actually. So we say, all right, that's u double prime times x e to the x. Okay, how about u prime? Well, there's a u prime there. and there's a u prime there. So there's 2. So what do we have? Well, we'll have 2x e to the x. And over here, we'll have 3 minus 2x times e to the x. Okay. And then, finally, the u's. All right, so there's 3 places where u shows up. And if you go through, we have an x e to the x plus 3 minus 2x times e to the x plus x minus 3 times e to the x. Now, you should hopefully be saying, ooh, very deja vu here, because that's basically this computation we just did before. By design, it will always happen this way. So we're like, cool, so we can just knock this part out. And now we say, hey, it's basically a simpler differential equation. So let's see what we can say here. Well, we have 0, it's homogeneous. That makes it really nice. Everything has an e to the x, so let's divide out by e to the x. So let's see, what do we have left? We have x u double prime from here. Here we have 2x e to the x. We're going to subtract 2x e to the x, which means that the 2x e to the x's actually cancel. Plus 3 u prime equals 0. All right, so remember, we divide out by e to the x because everything has an e to the x. That looks pretty simple. In fact, we don't even have to try very hard. So what can we do? We can move this across and then do a little bit of rearranging. So look, u double prime over u prime is equal to minus 3 over x. And now integrate both sides. Okay, so what happens if you integrate u double prime over u prime? Well, u prime is a function. U double prime is its derivative. So it's function downstairs, derivative upstairs, which means the integral is a natural log. So we're at the point where we have natural log of u prime is equal to, over here, minus 3 natural log of x plus c. Well, okay, raise both sides to the e power. U prime. Here we'll have this constant comes down. It's just a constant in front. And then we'll have minus 3 goes up. So log of x to minus 3. And then we apply properties of log 1 over x cubed. So that's u prime. So what do? We integrate again. So, all right, integral of u prime is u. So we get u. Here we have what? Well, you want to say, well, it's x to minus 3, right? So it would be x to minus 2, because minus 3 plus 1. Then he's going to say, well, minus a half c and plus d. But now we can do something. That minus a half is a constant. All right, just absorb it. So constant times 1 over x squared plus d. Now, is that our new solution? No. But it's almost our new solution. How do we get our final answer? Well, we have to multiply by e to the x. So u times e to the x would be some constant, e to the x over x squared, plus some other constant, e to the x. Now this solution we already knew about. That was the one they gave us. That is our new solution. And therefore, our answer is e to the x over x squared. There we go. Ah, good times, good times. Okay, number 7. Ooh, another problem where we have to verify. Okay, so verify that y equals 1 over x squared plus c is a solution to a differential equation. Now, that doesn't look so bad. Okay, so we're going to start with y prime. So we have our function y. That's x squared plus c to the minus 1, taking the derivative. So, okay, so chain rule. Minus 1 comes down. X squared plus c to the minus 2 times the root of the inside, which is 2x. All right, so that's minus 2x. And here, this is x squared plus c to the, if you like, minus 1 squared. We say, well, wait, that's just y. So that's minus 2x y squared. Right? So y prime equals minus 2x y squared. Works out. Okay, so we're done. Now, that's part A. Part B, so this has several parts. Set up a differential equation for a curve which would always intersect a curve from part A, so one of these curves, perpendicularly. So our new curve, regardless of when it hits this curve 1 over x squared plus c, it always does so at a right angle. So how do we do it? Well, there's a hint. Lines are perpendicular if slopes are negative reciprocals. So what we have, remember, y prime, rate of change of y with respect to x, also known as the slope of the tangent line. So that's the line that the function is locally approximated by. So if I want to be perpendicular to it, I just need to be perpendicular to that. So I say, oh, okay. So for part B, say, all right, I need to be the negative reciprocal. So negative gets rid of the minus, and reciprocal says, put it like that. Okay, so that's part B. That's actually not so bad. Really, this is more of a question, do you understand what things represent? And if you do, it's free points. And if you don't, sorry. All right. But that's our goal, understanding. Because we want all the points. All the points. All right. Part C. Okay. Solve. Well, that doesn't look so bad because it's separable. So, what can we say? Y squared dy is equal to 1 over 2x dx. Right? We move the y squared across, move the dx across, and that's the separation. Do the integration. We get 1/3 y cubed is equal to, here, 1/2 log x plus c. And now, all right, multiply by 3. Y cubed equals 3/2 natural log x plus c. Of course, the 3 can be absorbed into the c. And finally, we can take our cubed root. So y is the cubed root of 3/2 natural log of x plus c. And there we go. So the moral is, if you look at this curve for some choice of c, and that curve for some other choice of c, doesn't have to be the same c, and you say, if they intersect, which it may not, but if they do, it will be perpendicular. Guaranteed. That's what our conclusion is. Wow. Good. Wow. That was fun. That was fun. That was actually one of the first kinds of problems we did. It's almost like we want to remember stuff. We do. The more we remember, the better we'll be. Okay. Number 8. Find a constant coefficient linear homogeneous, our favorite kind, differential equation, for which y equals e to the minus x sine squared x is a solution. Now, you're probably thinking, wait a second. If I'm constant coefficient linear homogeneous, I can look like powers of x. I can look like exponential functions, e to some power of x, maybe times polynomial. Or I can look like polynomial times e to the x times sine or cosine. That's sine squared. That's not on our list of things that we are used to seeing. So, what do we do? Well, there's a hint. Think of other ways to write the function y equals e to the minus x sine squared of x. Now, this comes back to the mantra that you often see in trigonometry. There's a lot of ways to rewrite the expression. And so what we want to do So you want to say, we want to rewrite it in ways which are friendly to the kind of things that we show up in the solutions. So again, things that we want, or rather we like, what do they look like? Well, x to the power k, x to the power k, e to the ax, x to the power k, e to the ax, cosine bx, or x to the power k, e to the ax, sine bx. These are things which show up. So can we rewrite this in that kind of way? And if the answer is yes, we win. If the answer is no, it can't possibly work. But I'm confident we can. Otherwise, why would they ask us? Okay, so we think, okay, e to the minus x we like, we're happy with that. So it's the sine squared. So we start to say, what can we do with sine squared? If only we had a good trig identity. And then we're like, oh, we do have good trig identities. So, in particular, there's something called power reduction. So e to the minus x sine squared of x looks like the same thing as e to the minus x times 1 minus cosine of 2x over 2. So that says, hey, I can rewrite this as 1/2 e to the minus x minus 1/2 e to the minus x cosine 2x. And now we say, ooh. Now we don't have to actually make the ooh sound, but we say, look, these things here are on our list of things we like. Because when I write x to k, it could just be x to 0, which is 1. Exponential functions look good. Exponential functions times cosine looks good. So we say, okay. So now we say we want to have a differential equation which has e to the minus x as a solution. And we sort of say, okay, instead of starting with a differential equation, getting to a solution, we say start with a solution, work back to a differential equation. So we're going to identify the functions, which identify the roots, which help us find the characteristic polynomial, which help us find the differential equation. So e to the minus x, this would correspond to a root r equals -1. All right. Now, e to the minus x cosine 2x, that actually is a pair of roots. This comes from the complex roots. So this would correspond to the roots r equals -1 plus or minus 2i. So the 2 is because of the 2 on the inside. So we say, okay, we just need to find a polynomial with these roots. Well, that says r plus 1 is a factor. Now here, another factor would be r plus 1 squared plus 4. And just, if you're saying where did that come from, just sort of reverse the process, right? Add 1, get r plus 1 equals 2i, plus minus. Then square r plus 1 squared, and then is minus 4. So you get r plus 1 squared plus 4 equals 0. Okay, so this is r plus 1. Here, r squared plus 2r plus 5, if you were to expand. And now we expand again. So r times r squared is r cubed. R times 2r, 2r squared. R times 5 is 5r. 1 times r squared is r squared. 1 times 2r is 2r. 1 times 5 is 5. Okay, so, well, that leaves us r cubed plus 3r squared plus 7r plus 5. So this polynomial has the right roots, which leads us to these kinds of functions in our solution, and these kinds of functions give us e to the minus x sine squared x. So the last thing is, write the differential equation. Well, that's the easy part. So we'll get the third derivative plus 3 times the second derivative plus 7 times the first derivative plus 5 times the function equals 0. And we're done. We're done. Ah, what a fun set of problems. There were some really interesting problems that are slightly different than things we'd seen before. But, it's good to see different ideas. And it's also good to see the same idea in different ways. Because, it's like as we hold up our object and look at it in different ways, we really start to understand. And with understanding comes an improved ability to do. And, I hope you do well. Good luck on your exam. Take care.